morning. Welcome to reInvent. Oh yeah, definitely put on the, actually you don't have to, whatever you want. If you do put on the headphones and I'm speaking too loud or too softly, you have a volume button on the right side, I think. Let's say we're building a game. All of us are starting a new gaming startup, and we're going to create a massive online multiplayer game that, if we're successful, is going to support hundreds of thousands of users. So we're going to need massive scale, probably millions of requests per second. And we're going to have to maintain very low latency for our users to have a consistently responsive game. Otherwise, they probably won't play our game. We're going to use ElastiCache Serverless for Valkey because it provides predictably low latency and supports the massive scale that we need. Now, my name is Elad. This is Yaron. We both work for ElastiCache. And ElastiCache Serverless does take away many concerns that you have as a developer or DevOps. For instance, you don't have to worry about security patching. You don't have to worry about version upgrades. But most importantly, you don't have to worry about sizing your cluster, and you don't have to scale it when your application load increases. This session is going to talk about optimizations that are relevant for very, very high-performance applications. And the optimizations are going to be relevant both for ElastiCache Serverless, also for self-designed clusters, or even if you're self-managing your own fleet of open source Redis or Valkey. Valkey, in case you're not familiar with Valkey, it's an open source in-memory database. It was forked out of Redis when they changed their license. And Valkey has been adopted by the Linux Foundation, and it's maintained by a very big community, very active community, including some industry leaders and a few cloud providers, including AWS. Let's go back to our game. So let's start with a POC of our game, right? We're just in our labs now. We're taking a couple of clients, connected them to a Node.js server, right? Node.js, that's easy, that's fun. So we'll probably just store all the state of our game in memory, right? That would include things like where our users are, where the monsters are, maybe their health, things like that. And we're going to use some disk if you want to store some more persistent resources. For instance, our game maps, our castle maps, things like that, that don't change that often. And so our users, on the POC, our users are probably going to have just terrific latency, right? We're in the lab. What would we expect in the lab for latency? Any ideas? OK, so usually when networking is not a concern, you would see latencies of around 100 microseconds round trips. Most of this latency would come from the operating system, the network stack, the kernel communicating with user mode, right? So it's not really network latency here. It's mostly just the operating system. And when we go and access memory for our state management, right, reading state, changing state, we're probably going to have access times of a few tens of nanoseconds. So that means that we can actually go to memory many, many times before it actually impacts significant latency. Right? We could do it hundreds of times on a single user request, maybe even thousands of times without it impacting latency. This is very different when we talk about disk latencies. Right? Even if you have the best SSD, it's going to be a little less than 1 millisecond probably, but it's going to vary, right? Why is it going to vary? Because when you read an object from disk, you're not just doing a single access. Sometimes you're doing multiple accesses because disks store objects on different blocks, right? So disk latency is usually very variable, which we probably want in our application, yes, no? No, probably no, right? We don't want this variability. And so, I mean, for our game POC, we can probably just load all the maps when we start, keep them in memory, and then just use them there, right? But when we take this to production, it's going to be a little bit different. So now our users are on the internet. We're using multiple instances of our application because we want scale and we also want high availability. We'll probably use a bunch of availability zones to get that. And our resources, instead of disk, are going to be naturally placed in some database. So, but when we read the database, latency is going to be, again, very variable. Somewhere probably typically 1 millisecond to 100 milliseconds. And that's because traditional databases, whether it's a relational database or a document database, I mean, those usually use a combination of both memory and disk to deliver queries. And it's very hard to control where your queries are serviced from. It's hard to say, hey, everything must come from memory. And I guess that's where Valkey becomes very, very handy. Because Valkey uses exclusively memory to serve your queries, it provides you with predictable latency. And I think that's what we want for our game. By the way, for any application, it doesn't have to be a game, right? We chose the game because games are fun. But any application that needs millions and millions of requests per second, Valkey, on strict latency requirements, Valkey is very useful. Again, because of the low variability. I mean, Valkey uses memory, so most of the latency you'll see, it's not even coming from Valkey usually. The most dominant factor with Valkey latency is probably going to be the network, right? And so if you're on the same AZ as your Valkey node that you're accessing, you'll probably have latencies far below 1 millisecond, sub-millisecond latency. Now, it may be that your application needs to go from another AZ and access a Valkey node on a different AZ, and then latency increases slightly. And I'll dive deeper into these latencies in a minute. But what if, right? What if we could manage our application such that we're reading from a replica node that's on the same AZ? That way we can maintain, at least for our reads, we can maintain low latency for all of our application instances, lowering our P50 and our average latencies for application. Sorry. Let's dive deeper into latencies. So we're going to talk about, we're talking about milliseconds, we're going to talk about microseconds, and we're talking about nanoseconds. That's the world we live in. Let's start off with your users. When you have users coming over the internet, connecting to your application, usually or typically you'll see latencies somewhere between 20 milliseconds up to 100 milliseconds, maybe even 150. It really depends on when your users are, right? They could be very close to the data center with an excellent internet connection, and they could be very far away. They could be on another continent. So that's the variability we'll see. When we continue into the data center, if you're communicating between two servers in the same data center, latencies are going to be very, very low. It's very similar to the lab we discussed before. So network latency is going to be nanoseconds usually, and it's going to be around 75 or 100 microsecond round trips. Again, usually because of operating systems, right? You can optimize that using tools like DPDK maybe that optimize this kernel to user mode latency, but usually that's what you'll see, and these are very low latencies anyway. Now, when we go from one data center to another on the same AZ, we can expect latencies of up to 1 millisecond. In case you're not familiar with this, AZs usually have one or more data centers. They're not just a single data center. And these data centers can be miles and miles apart. So latency is slightly higher. And when you go over the AZ to another AZ, those data centers are even more far apart, right? And then latency can, in some regions, can be milliseconds. Now, the most dominant factor here is distance, right? We have to carry this signal over fiber optics from point A to point B and back, right? So we're bound by the speed of light. That's the thing. So if they're close, it's going to be good latency. If they're farther apart, it's going to be higher. Let me share some real life examples. I hope you can read this. I'll try and read this aloud. What we're looking at are actual latencies from US East 1 region. I took this a few days ago when I prepared the slides. And these are cross-AZ latencies. Latencies from AZ-A to AZ-B, AZ-1 to AZ-2, AZ-2 to AZ-1 to AZ-3, just a few measurements. And you can see, if you're unable to read this, most of these latencies are far below 700 microseconds. Right? These are the cross-AZ ones. So we said they could be milliseconds. In this case, in this particular region, and AZs, they're far lower. Let's zoom in now. What happens inside each AZ? There are latencies that are comparing inside each AZ. So there's latency from 2 points inside AZ1 and other latency from 2 points, 2 machines in AZ-B. These latencies are much lower, as you can probably spot, right? And most of them are around or below 100 microseconds. So excellent latency in this case. There is some variance here. It depends on which region you use and which AZs, where there's placed the distance between them. What you could do, these charts are not something internal to AWS. You can all view them. I see nodding heads. You know this. You can check out something called the Network Manager. It's available on your AWS console, of course, the APIs. And you can actually take a look at all the latencies between different regions, different AZs in those regions. And then you can look at your application and consider the factors that around latency here. What latency can we expect between AZs? What latency can we expect between regions? Any use case that you have. Moving on. You folks have tasked me with creating our first microservice for the game. And I didn't do an amazing job, spoilers. And I created this microservice for getting user profiles. Now, this is not a good practice. See if you can spot my mistake here. Okay, see some smiley faces. Don't laugh at me, right? So let's cover what we're doing here, right? This is a very simplified HTTP server. Whenever there's a new request, the first thing that it does, it goes and creates a new Valkey client, calls connect, and then does a get for the profile that we actually need. Now, the problem here, you can probably see it, is whenever we have a request, we're doing all these things just to get a single key, right? We're getting a new connection. That means DNS query. It means TCP handshake, TLS initialization. It means cluster discovery, doing cluster slots, understanding where everything is placed on the cluster, right? And then finally, what we actually wanted, which was getting the key, doing the get command. So I'm sure most of you have already know this, but the good practice is to use persistent connections, and that means just taking this connection initialization part, taking it outside. Oh, sorry about that. Now, I'm sure you know this, but persistent connections are extremely important, and you can actually do them even if your compute is Lambda. Some people don't realize it, but Lambdas, I mean, they don't actually get torn down after each call, right? They persist. If you have more calls, if they remain hot. So persistent are definitely useful both for EC2, ECS, Kubernetes, or Lambda use cases. But another important point about connections is to understand what happens when we do this good practice, right? So pipelining is another important factor that can influence performance, especially when you have a high-performance application. Let me explain. Pipelining, by the way, it means sending out multiple requests on the same TCP connection without waiting for responses. And this is exactly what's going to happen in our web server. Because take a look. What happens when a user 1, sends a request and the server reads it? It read the request. It's going to shoot out a GET command to our Valkey, right? Now, this is asynchronous, right? We're doing an await here. That means that execution waits, but the server is not blocked, right? It can continue servicing more requests in the meantime. So another request is read from user 2. And what happens? It gets sent as well, and user 3, and it gets sent as well. So now we have a pipeline, even though I haven't written the word pipeline anywhere on this code, right? It's kind of an implicit pipeline, and that's what happened. And don't get me wrong, pipelines are great. Pipelining is an excellent way to increase latency with Valkey or open source Redis, because it's kind of, when you send things in batches, the server has to do less work in order to service them, right? Less I/O. Maybe they can read all the requests in a single I/O operation. I think the problem is when these pipelines, when you have very high performance, and our game is going to have millions of requests, and the concurrency is going to be very high for each of these application web server, and then what happens if this is not 3 requests at the same time, but 1,000? And that's where things get a little bit dicey. Let's zoom into the TCP connection. So we had request number 1, user number 1, request for user number 2, request for user number 3. Now, the REST protocol for both Valkey and open source Redis is ordered. That means that responses must arrive in the same order as the request that we send. So very susceptible to head-of-line blocking. What happens if user 1 requested a very, very large profile? We have to read all the response for user 1 before we read the response for user 2 and 3. And so that response for user 1 is literally holding the head of the line for us. And again, with small numbers, it's not significant. With large numbers, more so. And there's another problem. What happens if we run into packet loss? Should we even, we're using TCP. Should we even worry about packet loss? No, yes. So, TCP does guarantee delivery. The only problem is that retransmissions in TCP take at least 200 microseconds to happen, right? That's hard-coded on the Linux kernel. It's not something you can do without rebuilding it yourself or something. So if we are having these large requests or just a request that's not large, and there's 1,000 requests waiting behind it, and there's a packet loss, all these requests, all these users are going to have a major impact. Now, packet loss is a fact of life when you have a distributed system, right? We cannot avoid it, but we definitely want to reduce the impact when it happens. And the way to do that is to use more connections, right? We can use more connections from the same application, thus limiting the concurrency on each of these connections. And that helps us minimize the blast radius whenever there's a large response or something like that. We can even think about things like, hey, if I know this type of request is going to be slower, I can maybe place it on a dedicated connection. That's another idea you can consider. By the way, another very easy way to reduce concurrency on each connection is just to scale out your application, right? The more application instances we have, the less work each of them needs to do concurrently. Of course, that comes with a cost. But let's talk about connection pooling. So connection pooling means using multiple connections from the same application instance. Some Valkey and Redis clients have connection pools built in, but many of these clients, especially the asynchronous ones, don't. They actually use a single connection and kind of multiplex requests in that connection. And so what we could do, if we actually need high concurrency, right? If you're talking about millions of requests for application, and we have high concurrency over a single connection, we can actually build them ourselves. And for our game, we can build something like this. Notice what I'm doing here. Instead of creating one persistent connection, I've just looped and created a bunch of them. And whenever I want to use a connection, I need to pick one, right? I can choose. So in my case, if you'll notice here, I've done a modulo over the user ID just to kind of load balance between these connections. But you can do randomization as well. You can do round robin. You can modulo over something else that makes sense for your application. OK. So everything is fine. Our game runs perfectly. Our cluster is very healthy. It has a lot of total resources, right? We have enough total memory, enough total CPU, enough total network bandwidth. Everything is peachy, and then suddenly it's not, right? Even though we have enough resources, we have an alarm. Our latency is spiking. Our throughput is reducing, and we're trying to scramble to figure out what happened. And a lot of cases, what happens is that we can run into hotspots. Hotspots mean that a lot of your traffic are hitting one particular node in the cluster, right? And that's usually because you have hotkeys. So you have a key that's very popular, and you need to read it a lot of times. But with Valkey and Redis, it doesn't matter if it's serverless or not serverless. Each shard actually owns, each key is owned by a single shard. And so, I mean, if this weren't, if we're diving into the metrics to understand what the problem is, let's say we all went through the metrics, we reached the network bandwidth case, we see all of the shards do kind of moderate bandwidth network bandwidth, and one of them is significantly higher, and that's probably a good indication of a hotspot. Now, what happens here? When we, all of us, dove into and debugged our situation, we found that we have a particular castle map in the game that's 100 kilobytes in size, so not very huge, right? And it's very popular. Users love it. That's a good thing. And we have to read it a lot of times. But the problem is that, say we didn't choose ElastiCache Serverless for this particular example, we chose an instance for our nodes which has 937 megabits per second bandwidth, right? If you calculate and you divide it by 100 kilobytes, you can only do around 1,000 requests per second for this object. I mean, that's extremely low for Valkey, right? Just 1,000 requests per second. And so the most obvious thing that we can do in these cases is probably to just scale up our nodes, right? We take the nodes, we replace them with larger instance types, let's say twice as large, so we get twice the bandwidth, and we can do, instead of 1,000, we can do 2,000. But of course, this comes with a cost. And also, by the way, with serverless, you don't have to worry about this particular, about scale up, because serverless automatically scales your instances up in place, and Yaron is going to dive deeper into that in a minute. But I mean, even with serverless, what if you don't want X2? What if you want X4? What if you want X10 or X50 or X100? We're not going to find an instance types with that much network, right? Just doesn't exist. So what can we do? One nice mitigation that we can try is we can duplicate our object, right? We can take our castle map, or all of our castle maps, and we can create copies of them. Now, because each copy is a different key, it gets placed in a different shard. And now, whenever we read a castle map for application, we can choose which copy to get. And now we're spreading the load. We're kind of load balancing the load of reading these objects between different shards. Now, think about it. With serverless, it automatically scales. and it can reach hundreds of nodes. That means that if you do 100 copies of your object, if you need 100 copies, you'll get 100 times your throughput. Another thing that we, of course, can do, we can read from replicas. Right? If we can read from replicas, we have more nodes kind of participating in our load balancing. Let me show you a very naive example of code for this. We have our castle cache. And when we read, what we need to do is to choose one of our copies, right? So we're choosing a copy. And here, I choose to modulo over the application worker ID. It helps me maybe with data consistency. But you can randomize. You can do round robin. You can do whatever business logic makes sense for your applications. Do you folks already see the caveat here? What happens when we want to update the castle map? We have to go and update all the copies, right? So if there's 10 copies or 100 copies, we have to do 100 writes. So, and this really works great for situations when you have a lot of reads, but not as many writes. That's a very common use case, right? This is super helpful, or it can be. But if you do have to do a lot of reads and writes at the same kind of frequencies, this won't work for you. So we have another mitigation that we can try. It's a little bit more work on our application, but we can actually break apart our object into smaller ones. So for our game, we can take each castle and maybe break it down into rooms or areas. And now, when we want to read them, we can actually pipeline multiple reads, get all the parts for our castle, and then assemble them on the application side. And now see how the load is, again, spread over more shards, kind of mitigating the hotspot. And if we can do further optimizations for application, we can maybe we can, down the line, write logic that we don't need to get all the rooms for a particular user. We can just get a subset or things like that. And of course, you can use your imagination outside of this game example to see how you can break apart your object in your application. Right, now let me turn over to Yaron, who is going to tell you how we designed ElastiCache serverless, how we're doing all this automatic scaling. Thank you.
Thank you, Elad. So a moment before I dive deep into the serverless and the way that we build all the technology behind the scenes, Elad mentioned multiple challenges that we need to take care when we build an application, specifically if we build them for high scale. So I want to tell you with ElastiCache serverless, you don't need to worry about capacity planning or right sizing your cluster. You can still achieve millions requests per second with a sub-milliseconds response time just using by ElastiCache serverless. Now, when you create an endpoint to ElastiCache serverless, automatically we are distributing all the infrastructure of the serverless across multiple availability zones. We do that first for high resiliency, high availability, but we also do that to achieve a very good performance and to reduce the latency. I will show you in a moment how it's happening. So once you create your endpoint to ElastiCache serverless, you connect from your VPC using a VPC endpoint to the ElastiCache serverless VPC. At the beginning, you're going to reach the NLB, and the LNB are responsible to balance the traffic across the serverless proxy. Now, I'm going to talk about the proxy in the next few slides and to explain why we build the proxy. But overall, the main job of the proxy is to route your request to the correct cache node. Now, we also know to locate your local proxy that sits on the same availability zone so you can reach the minimum latency while you connect to ElastiCache serverless. So as I mentioned, the proxy is responsible to route the request to the correct cache node, and to do it very, very effectively. The reason that to do it effectively is because we are using a multiplexing technology, multiplexing protocol. We actually use a TCP, single TCP channel to connect the cache node, while we are moving on that TCP channel multiple different connections of clients. And in that way, we are reducing the number of connections, and we also reducing the number of system call upon every network transaction. Now I want to move back to the cache node itself. We are running on a multi-tenant environment. We are running on a physical host that we are constantly monitoring all the time. We have a service that we call it heat management. And the job of the heat management is to monitoring the cache node, all the physical hosts across our fleet. Now, because we are running on a multi-tenant environment, we are sharing resources like CPU, memory, and networking. And the cache nodes running inside the VM within the physical host. And as you can see, each cache node has a different size. And the reason for that is because each cache node has a different workload to digest. Now, our job as a serverless is to make sure that you have the enough extra capacity to run your workload. So I mentioned before that we have the heat management process that run and consolidate all the physical host status across our fleet. And because we are constantly monitoring and making sure that you do have enough resource to run your workloads, we are, in some situation, we can find physical hosts that reach to some threshold. For example, in here, what you see, we reach to some threshold of memory and network. And we need to start to think how to move to evict some of the cache node from this physical host to a more available physical host. So we are using the algorithm of the power of the two random choices. We actually pick into the two most hottest cache node, and we are choose to move only the second one. The reason that we are choosing to move only the second one is because we don't want to interrupt the most busy one that probably going under heavy load and start to with maybe scaling operations. So we want to let them succeed, but we still want to move the one that will release enough resources once we move him to a more available cache node. Now, Elad, before that, explain you why it's so important to have a persistent connection. There is a cost when you create a new connection. And with the proxy, we promise you, while all the changes happening behind the scene, to store your connection and to have it persistent to the ElastiCache serverless. Of course, the proxy will also be responsible to move the connection to the new created cache node, the one that we move to a different physical host. And in that way, we are keeping all the fleet very balanced with all the enough resources that is required. Now, there are some situations that you cannot wait for the heat management to free enough resources for your workload. And you need something more drastically. You need to handle a burst of a workload that kicks in because of event or something that now is happening in your business. And for that, we build a very nice technology in the ElastiCache serverless to support that. We are actually using a platform technology that does not have a fixed memory or CPU footprint and can be rescaled up and down very instantly. We are using a technology that this technology based on a multi-tenant environment, so we can keep the cost very minimal. So this technology allows us actually to scale up very quickly and to use the more cores and memory that we have on the physical host. And actually, we can support 8 times more throughput on demand, while once they are kicks into the serverless technology, serverless endpoint. Now, because we start with scale up, now we have time to start the scale horizontally, scale out. And the way we do that, there are three main stages. We have the detection, which is happening very quickly. We also have the ability to project the upcoming workloads, because we are constantly monitoring your workloads, and we know to predict what would be the workload in the next coming minutes. So we can pre-scale your cluster behind the scene and be ready for the workloads that can come. Now, the second stage is the provisioning. To provision a new node is very costly, but we are using a worm pool. Worm pool is list of cache nodes, predefined, pre-installed, that waiting to be attached very quickly to the cluster. Now, once we use the worm pool, we are attaching them to the cluster, and the last phase that now is required is to move the data from the original shards to the new shards that we just attached. So for that, we are monitoring the data within the slot, and we are capable to determine which of the slots are considered as hot and which of them are cold, and based on that, we can decide which slot we want to move to which target. We can do that in parallel within the slot, so we can move them very quickly, and we can do it in parallel between the different targets, so we can actually assign multiple targets to our cluster and to transfer the data in parallel, so the scale out happens so quickly, so we can double the cluster throughput every 2 minutes. Now, I promised that I will speak about the proxy and the reason why we build it. First, we decided to have a single logical entry point to the serverless cluster. And for that, we build a proxy. The proxy main job is to route the request from the client application to the cache node. So it's actually encapsulate all the underlying cluster topology, everything that's related to failover, disconnection, scaling, everything is happening behind the scene. So your application can consist with a single connection to the proxy, while the proxy will maintain thousands of connections behind the scene to the cluster, and you don't need to be careful about that, because you can scale your throughput very instantly using this proxy technology and all the scaling that I mentioned, so you can jump from 0 to 5 million requests per second in only 12 minutes. Now, if your application is latency sensitive and you don't have a strong consistency requirement, you can use the read from replica that we also have it on ElastiCache serverless. Every time that you create we create one primary and two replica as a beginning of the shard. Now, if you want to connect to the replica, the only thing that you need to do is to flag the connection that you want to read the data from the replica, and the proxy will do it for you. Another thing that the proxy will always make sure to do is to read always from the local availability zone. So regardless if it's primary or replica, the proxy will make sure to read the data from the local AZ, so you can achieve the microseconds response time. Now let's take a look how to build the code so we can see how simple is it to work with ElastiCache serverless. So here in my code, I'm just connecting to my ElastiCache serverless. I'm using TLS enabled because always when we're running on serverless, we support only TLS connection. And here I'm flagging on that specific connection. I'm telling to the proxy, I want this connection also to read the data from the replication so I can scale the read throughput, and I can also achieve the sub-milliseconds response time. Here I have three very simple block of codes. The first one, just populate a few keys to my cache nodes, to my cache serverless. The second one is a for loop that I'm fetching the data from my cache node. And the third one is pretty the same, just with pipeline. I'm doing a batch of multiple keys that are running all together. Now, as simple as that is that we are going through the proxy. Now, the proxy will make sure that to spread the request to the correct shard behind the scene. It will also promise me that if there is any disconnection, scaling that happen in parallel, failover, nothing will disrupt my connection. Everything is happening because the proxy will take care of that. And the most important is that the proxy will promise me to read the data from my local availability zone. As you can see, the beautiful thing here is that my code stay clean. I don't need to worry about that. I don't need to put any special code to do that. Everything is happening and doing and managed by the proxy. Now, I want to go back to Valkey. Elad talked about Valkey. All the example, all the technology that we build here is based on the Valkey. And I want to show you how we leverage the Valkey technology even to improve the serverless scaling that we offer today for our customers. So I want to go back in time and to see how Valkey started. Valkey designed as a single-threaded process. And the main reason for that was simplicity. Because there is no race condition, no synchronization is needed, and you can still scale out and to use the shared nothing architecture and to improve the cache coherency. With this technology, we can achieve around 190K requests per second, and 50% of the time we're going to be busy on I/O, on read and write. Now, to simulate that, we have the main thread. Every time that another workload comes in, it's wait on the pipeline for the main threads to finish the processing of the workloads on the queue, which eventually what's happening is that we have kind of head-of-line blocking that Elad showed you before. Later, Valkey introduced the I/O threads. And the main idea behind the I/O threads was to offload all the I/O requests to the I/O threads itself. Simple idea, does the double the performance, almost close to 400K requests per second. And this time, we are now more busy on the process command. 50% of the time, the process itself was busy on that stage. Last year, specifically AWS and my team, contribute to Valkey the new I/O threads architecture. The idea is very simple. We have the main thread that orchestrates all the jobs that span the I/O threads. Now, he ensures that there is no race condition, and the number of I/O threads can be adjusted according to the workloads that running on the hardware itself. Now, despite of the dynamic nature of the I/O threads, the main thread also responsible for the affinity. And he also always makes sure that the data is assigned to the specific thread. So we can also enjoy from cache locality and to improve the performance. So with this ability, we can achieve even more than 1 million requests per second for a single instance. That was a huge win for Valkey. So just to simulate that, now we have the main thread running. And every time that we need to spawn another I/O thread when a workload is coming in, we just spawn it out. We can process the workloads in parallel, and we can remove some of the I/O threads and to release some of the compute once the workload is relaxed. Now let's see how everything is playing all together. We talked about the wormpool. We talked about the proxy itself. We talked about the physical host that we're running on a multi-tenant environment. And here in my example, I have a cache node running with 2 cores, 2 I/O threads. Because we're running a very steady state of 30K requests per second, this is the throughput. But now let's assume that we have some events that kicks in. And our customers expecting us to grow our instances very instantly. So immediately, we can scale our throughput by 8 times because we assign more cores. We are spawning more I/O threads to the cache node. And in that way, we can scale up. In parallel, in the meanwhile, we are just assigning more cache node to the existing cluster because we are using the worm pooling. The proxy automatically going to detect that. And all that happening in parallel because encapsulated from our application. we started to move the data from the old shard to the new shard, and in that way we can scale the throughput, double the cluster capacity every 2 minutes, and achieve a very seamless serverless experience. Now, I have here a pre-record demo, nice demo, that we started with adding more workloads to the cache serverless nodes. As you can see, I started with 250 K requests per second, and I'm going to add more and more clients and workloads to my cache serverless nodes. Now, in the meanwhile, while you see that the throughput is growing, my P50 latency is stay below the milliseconds response time, which means we are still having the microseconds response time, even when we push in more workloads to the cache node. As you can see, I'm already achieved the 1 million. I'm more than 1 million requests per second, and the P99 is going to jump to 3 milliseconds, and this is because we started to move things. We are using more IO threads, we are using more hardware resources, so it might impact the P99 latency, but the P50 will stay below the microseconds, and the P99 will saturate it while we finish with all the scaling process. So the demo will run until we reach to 3 million, but we don't need to wait until that. Now I want to recap and to talk about few best practices that we learned for today. So we talked about connection pools, persistent connection. Every time that we establish a new connection is in order of magnitude more expensive compared to simple get and sect command of Valkey. So using a connection pool, using a persistent connection, long-lived connection is very important. We talked about reading from replica to scale the read throughput, to achieve high availability and resiliency. And specifically for serverless, it will benefit you to achieve the microseconds read response time. We talked about hotspots. We have two mitigation for that. Specifically, we talked about, Elad mentioned about the key duplication, that you can duplicate the keys and read and use all the hardware resources that you have on your cluster. We talked about the key splitting, that you can split a specific key across your shards and to read even more throughput on that specific key. And related to that, we also, as a key principle, we say limit your size of your object. Because eventually, if you have a very large object, it will consume processing time and CPU. And also the payload itself, it can also reach you to a situation that you're going to exceed the network baseline. Because we are talking about caching, one of the most important principles, how you can save your memory more freshness, more close to the original, without a stale data. And also, specifically with serverless, it can also help you to reduce the cost. So time to live, expiry, is one of the ways to do that. You explicitly assign them to a key or set of keys, and you can use a relative time or absolute time. But one of the most important, if you're going to use it, try to use the random jitter when you delete them, because once they all going to be deleted, we don't want them to be deleted on the same period of time. Make your Valkey very busy with that. We want to spread it across time window. That was all today. Hope you enjoyed the session. Thank you very much. Me and Elad will stay around. You can talk with us and ask questions. And I hope you enjoyed that. Please fill the survey and tell us how you enjoyed for the session. Thank you.